Hello and welcome to my channel. This is the second video of the lecture series, the tutorial series in which I am teaching the COMSOL Multiphysics for beginners. The agenda of today's video will be what is COMSOL, what can we do with this software, and after that COMSOL capabilities, and then steps to use this software. So let us start. What is basically COMSOL software? Now, COMSOL Multiphysics is a simulation software used to model and analyze real-world engineering problems involving multiple physical processes, also called a multiphysics problem. So what COMSOL basically is, it's a software, both it is a modeling and simulation software, like I uh, taught in the last video. What is modeling and what are its various types, what is simulation and what are its various types. So this COMSOL software, it has both the capabilities, that is the modeling as well as the simulation. So this software is used to make a model and then analyze the model, make a model of the real world application. We have any practical system in front of us, depending upon the physics involved, like it is a heat transfer problem, or it is a fluid flow problem, or it is a structural mechanics problem. We can solve any of these problems, and even we can solve a problem which does not just involve one physics but two or more than two physics. That's what multi-physics stands for. It couples the different physics together very easily and is able to solve that complex problem. So it is a simulation software used to model and analyze real-world engineering problems, so involving multi-physical processes. Especially this software is designed to solve those systems which involve not just one physics but more than one physics. For example, water is flowing through a pipe and it is getting heated on one end. So it is getting heated on one end. Hot fluid has to be carried from one end of the pipe to the another end, and we want to analyze this system. Now, if we see this system, there are not just two but three types of physics is involved. Number one, the fluid is flowing, so fluid flow physics is involved. Number two, heat is involved. Heat is transferred from some source to the fluid, so it is a heat transfer problem as well. So another physics is involved. Then there is third physics involved, in which we want to have a good strength pipe, a stronger pipe, which can carry the required amount of the desired amount of fluid from one end to another end. So it should have a good amount of strength. So structural physics is involved. So problems, systems, practical systems which involve more than one physics can be tested through computer, which the word we use for that is the simulation. Though, so such systems are simulated, uh, which involve more than one physics using the COMSOL multiphysics. Now there are other softwares in which we can solve such problems. How COMSOL multiphysics is different from them, and why should we choose multiphysics over them? So for example, the first problem that comes in mind, first software that comes in mind is ANSYS Workbench. Now that is a industrial level software, and it also has a module of a multiphysics which couples different physics together. But that is one module of that software. If we talk about the COMSOL multiphysics, it itself is a software that is basically designed to couple different physics together. It is fundamentally designed for coupling different physics together in an easiest way. we can say. So COMSOL Multiphysics is a simulation software used to model and analyze real-world engineering problems involving multi-physical processes. Also, we call them multi-physics problems. Now, it is widely used in academia, it is used in colleges, it is used in universities, it is used in research institutions, and it is used in industries for simulating physics-based systems using numerical methods. It uses numerical method to solve a real-world problem, and COMSOL uses finite element method. Now, what can we do with this software? Now, we can solve many problems using this software, and those problems can be from different fields or can involve, as I said, more than one physics at the same time. For example, we can solve heat transfer problems. A system involves conduction heat transfer, it involves convection heat transfer, or it involves radiation heat transfer. We can solve any heat transfer problem using COMSOL Multiphysics software. Number two, fluid flow problems. Whether fluid flow is modeled as laminar flow, it can be solved. Whether it is modeled as a turbulent flow, we can solve it using the COMSOL multiphysics. Whether the fluid is Newtonian or the fluid is non-Newtonian, we can solve those problems as well. And uh, if a system involves a single phase fluid like pure water, not not steam mixed with it, it is air, so those are the single phase fluids. But if a system involves multi-phase fluids, boiling water is flowing from one end to another end, so it is not just a single phase is flowing, multi-phase is flowing, the liquid phase as well as gaseous phase together. We can solve those multi-phase problems as well. Now coming to the another field, we can solve structural mechanics problems. We want to analyze stress in a body, how much body deforms under certain loading conditions, the vibration is that a member of a truss of a, or any structure is vibrating under some fluctuating loading or something. We can analyze such things. Then electromagnetic problems like alternating current, DC currents, microwaves, optics, RF. We can solve electromagnetic problems as well. We can solve chemical reactions and mass transport. So mass vapors, or suppose water vapors are uh, transport, they are getting transported from one end to another, and from one medium to another medium. We can solve those mass transfer problems. The chemical reaction is a chemical A is reacting with chemical B giving product C, and we can solve those kind of problem, how much heat is produced or whatever the problem is. Then we can solve the acoustics, sound related problems, piezoelectricity, materials on which pressure, by the application of the pressure, the voltage is in a developed voltage is induced. We can solve such kind of problems. Battery modeling we can do, and much more. These are different physics that, and many more physics that we can solve using COMSOL multiphysics, and even a problem that involves more than one of these physics together, we can solve those problems, because COMSOL multiphysics couples these physics very easily. Now, multiphysics capabilities. What makes COMSOL unique is its ability to couple different physical phenomena in a single model. So, for example, like I said, water is flowing in a pipe. It is getting heated on one end, and the hot water generated is getting transported to the another end. So, this is a real world problem in which three physics are involved. For example, as I said, heat transfer is involved, fluid flow is involved, then structural mechanics is involved. We can study all the three physics together using COMSOL multiphysics. This is its multiphysics capabilities, and it does so very easily, unlike other softwares. Now, simulating heat transfer in a moving fluid, conjugate heat transfer. Now, heat transfer in a moving fluid, as I gave the example of, it is a multiphysics problem. Modeling electrothermal mechanical systems in devices like MEMS. So these are the mechanical micro. MEMS stands for micro electrical mechanical systems. These are the microscopic devices, miniature devices, which couples the electrical and mechanical systems together. So we can model these devices. We can simulate moisture and heat flow in building materials. In building materials, we want to simulate moisture transfer and heat flow together. So moisture transport problem, moisture transport physics is involved, heat transfer is involved, or even we can study the airflow as well with it. So third physics, that is the fluid flow, is also involved. So the COMSOL multiphysics has multiphysics capabilities which we can solve very easily because the software couples those physics together very easily. Now, steps to use this software. Now, what are various steps that we can follow to use this software? So let's take an example. For example, here's a problem of a structural mechanics problem. So what this problem is, it's a simple prismatic bar, a simple cylindrical bar on which axial load is acting, and on the other end it is fixed with the wall. So what we want is, we want to analyze the stress distribution. We want to analyze the stress distribution uh, within the material, within this prismatic bar. So how can we do this? Now, when we study this kind of problem, what we do is we start with like, so first of all, we know what our geometry is, cylinder here, and we know this cylinder is made of, say, like structural steel or anything, copper or whatever. And then we know already these two because we have a bar in front of us. We know the amount of load that is acting on the prismatic bar, which is, say, here F, and we want to study the stress. Now, how do we study this stress? So we have this prismatic bar, and on which axial load is acting. So how do we analyze this problem? We calculate the normal stress, which is force divided by its cross-sectional area. And suppose there is another kind of loading acting on it perpendicular to its axis, so it will make it to bend. So there is the bending stress. So, and we know this bending stress is something like my divided by I, and which is the bending moment, and y is the distance from the neutral axis, I is the moment of inertia. And suppose there is torque acting on this bar, so there will be torsional stress. So torsional stress will be like torque radius divided by j, polar moment of inertia about its axis. And suppose also load is acting perpendicular to the axis, which is trying to break it because it is fixed on the another end. So shear stress. So shear stress we will calculate using the formula VQ divided by BI, where V is the shear force, Q is the first moment of area, which means area times the distance, then B is the width, and I is the moment of inertia. So these are the various kinds of stresses that we can theoretically calculate using these formulae. And finally what we do is we calculate the von Mises stress. Von Mises stress is used to find the failure criteria out of these all these stresses. How we, first of all, what we do is we calculate the total normal stress, which is the normal stress plus bending stress. Then we calculate the total tangential stress, which is the torsional stress plus shear stress. Then we total. Then what we do is we calculate the von Mises stress using the formula square root of uh, total normal stress square plus 3 times total tangential stress square. This is what we call as the von Mises stress, and this stress, this final result makes the failure criteria. So this is the final failure criteria, and this is the final stress which we use to design this prismatic bar. This stress will tell us if stress is large, it will tell us either we have, if stress is large, to to uh, to have large loading on this prismatic bar. So in order for this prismatic bar not to break, not to fail under the given loading condition, we want it to be stronger, because the stresses are, suppose if the one stresses come out to be larger, we want it to be stronger. So how to make this prismatic bar stronger? Either we increase the thickness of the bar if we can't change the material, or we use the stronger material. So this is how we analytically analyze this structural mechanics problem. Now, if we move back, same problem we can solve using COMSOL multiphysics. So what we do is, now when solving this problem analytically, we know this, or testing it practically in the real world, we already have a prismatic bar, we have its shape, we already have its material, we apply the load, and we put the sensors on it and calculate the various deformations. Based on that, we can calculate the strain developed, the stress induced, all that. That's how we practically do it. But using computer, we don't have anything. We want to model everything. We have to make every detail, we have to give to the computer in order to test this using the computer, which we called simulation. We want to, in order to simulate this, we have to feed the computer each and every problem. So how do we do in steps. First of all, select the dimension. First of all, you have to tell the computer what dimensional problem this is, because if it is a one-dimensional problem, it will be much simpler. If it is a two-dimensional problem, the things will get complicated. If it is a three-dimensional problem, it will get more complicated. Computer has to solve more number of elements. That's why we have to initially tell the computer that which dimensional problem this is, to make it easier for the computer to solve it. So first of all, select the dimension. So we will tell the computer that this is a cylinder, which means it is a three-dimensional shape. So our problem is three-dimensional. So our problem is three-dimensional. We'll tell it is a three-dimensional problem. So we'll tell the computer that it is a uh, three-dimensional problem. So we have to start with a 3D problem. So step one, we told the computer is a three-dimensional problem. Now number two, choose the physics. Now after that, we know, when we tested this, we know we have to test it for stresses. So it is a structural mechanics problem. So but we have to input every detail to the computer. So we will tell the computer it's a structural mechanics problem that we are solving, because it will have the structural mechanics equations in that option, structural boundary conditions in that option. So we have to choose accordingly. We have to choose that special kind of physics in which those structural mechanics equations will be integrated, will be built in, the boundary conditions will be built in. So we have to choose the physics. We will tell it is a structural mechanics problem. So 3D structural mechanics problem. Then study. Now now we can see there are like two types of studies. There may be more, but in simple words, we can say that studies are of two types. One, we want to study the stresses with time, which changes with time. Suppose this our force here, it is changing with the time, which means the stress that gets developed, that gets induced in the material, they will also change with time, because the loading is changing. So when we study such kind of problems which involve change with time, or like that, we call it the a transient problem, or dynamic problem, transient study. And if we want to we have a constant loading and we want to analyze the stress, no time in our foot does not change with time, so it is a steady or stationary problem. So we have to, after that we have to tell the software that which type of study we want to do, whether it's a stationary study or it is a transient study. Then accordingly we will choose that type of study. So the computer will start accumulating the information related to the dimension, related to the physics, related to the study. It will start, when we input those options, it will start accumulating those kinds of features at one place for us that we can use to solve this problem. Then we have to tell the computer that it is the geometry, what kind of geometry it is. Since by looking we know that our system has a cylindrical shape, so we have to input the geometry. So we will tell it that the shape, our shape is cylindrical, it is a cylinder, so geometry is fed in the system, in the computer. Now we have to tell it, as I said, we have to input each and every detail to the computer in order to solve this problem, because it can't like see the practical system like we can see with our eyes, we can feel the material and all that, and we know all of those things and we just apply the formula. But to computer we have to input each and every detail. Now choose the material, we have to tell the computer that it is made up of structural steel or whatever the material is, structural steel. These are various steps, so this step is done. Then we have to tell the computer, okay, now what kind of boundary conditions are there, means what kind of forces we are applying, based on which we are calculating the stresses developed. So we know that the prismatic bar is fixed on one end, so under boundary conditions we will apply a boundary condition for this, that's called fixed constraint. Fixed constraint, that means one end is fixed. So we will select in the computer we will select this end and we will apply fixed constraint, means this end of the bar is fixed, we are telling the computer. Now on the other end it's not fixed, but loading is applied on the another end, so we will apply another boundary condition, and the force is being applied on the another boundary, we will call it, we will apply the boundary loading, boundary loading or boundary force. This is the another boundary condition. Now we are telling the computer that one end of the prismatic bar is fixed and the another end of prismatic bar is being applied with a force. Now till now the computer knows most of the detail of the problem. It knows the geometry, it knows the physics, it knows the study, it knows knows the materials involved, it knows the boundary conditions. So the computer is ready now to solve these equations that are integrated in this physics, structural mechanics, like those equations that I showed in the whiteboard. So those types of equations are also already integrated or inbuilt in the physics. So it will try to solve those problems using forces that I loading the with using the geometry. I would have put the area, the length, the radius, and all those features. It will use the loading, it will use the area, it will divide the load by the area, and it will calculate the normal stress and all that. It will calculate the bending moment, then use the distance from the neutral axis, and then divided by the moment of inertia, which has its own formula, and it will solve for us. now now it what now how the computer solves this problem is called a numerical simulation. And for numerical simulation, meshing is important. What it does is it breaks the whole domain. Our domain is this prismatic bar. It does not solve the entire problem on this prismatic bar. What it does is it divides this whole domain into smaller elements, very smaller elements first, then apply the equation at on one element using the boundary condition. It will apply it on this element, then it will solve it and calculate the stress at all points. then it will apply that information as a boundary condition for this element, solve for this, and likewise it will go on solving for each and every element, and it will accumulate the results for each element, and that way we will know how stress varies, and that way we will get to know how stress varies along the prismatic bar. It will give us all the small gradients in the material, because we are solving for each element separately these equations. This process is called meshing. So finer the mesh means smaller these elements, the mesh will be finer, and finer the mesh, uh, the software will obtain all the details, all the gradients. It will give us all the changes that is happening within the material when it comes to stress. It will capture all the gradients if the meshing is finer. If we choose coarser meshes, suppose this is a bar, and if we choose larger coarser mesh, which means larger elements, so it will consider for each mesh element, it considers the stress is uniform in that element. It is in uniform in that element, in this uniform in this element. So it will not it will not capture the full detail. Suppose suppose this is one element, and stress is varying like this in this element. So if the meshing is coarser, if the mesh element we have chosen larger, it will consider that the stress is uniform in this larger element, and then it is changing from this element to the next element. But actually stress gradients are very large, so it is changing within each element also. If we change larger element, it will not capture this detailed information. So the more detailed, the more finer the mesh is, the more accurate the results are, the more real stress changes it will capture, the stress gradients it will capture and give in the results. So this is what meshing means. Then after that we have to tell the computer which kind of mesh it can use. If the suppose if our system is simple, it is regular shaped, so and the property is not varying so sharply, it is not varying that much, so we can use coarser meshes. But if we want to capture the details, then we have to use the finer mesh. So for meshing purpose we have to go for coarser to finer, and in this direction the accuracy increases. The results get more accurate, and the software captures more and more detailed stress analysis or the temperature gradients. Then when we use the meshing, after that what we do is we start testing. It's called a run the simulation. Then we press the study we press the option in the console, it's called a compute. Then we press the compute, and it will start testing. It will start running, take its time, solve all the equations for each element separately. When it solves for each and every element of this prismatic bar, then the simulation will be completed and it will show us the results. Then we will get the results, and using the results we will be having like sigma stress values. We will be having the normal stresses. We will be find the bending stress. We will find the torsional stress. We'll find the shear stress. All those results we will all this data will be tabulated. Then we can post to process these results. We can add these stresses like we had to do to calculate the to calculate the total normal stress, like sigma normal plus sigma bending. Then total shear stress, like torsional stress plus shear stress. Then in post processing we will add them. We will calculate the von Mises stress. For that we will do sigma square plus 3 times tau square, and this we will use for the failure criteria, and this will tell us what is the critical stress in the prismatic bar and what material or what thickness we should choose for it, so that it will keep functioning, keep working where it is used without failure. So this is how COMSOL multiphysics problems are solved, by going through these steps one by one. Now in the next video, I will start with the introduction to the software, how the software is opened, how we can select the dimension, how we can choose the physics, how we can choose the study, how we can select the geometry, and we will start exploring these options one by one in the later videos. Till then, thank you.